Welcome to another episode of Champ and Coach Bowles Teach Aquatic Science. This week we're going to be learning about ocean currents and tides. We are going to start this lesson with talking about different ocean currents. So a little bit on current history. Get it? Current history. But sailors used to think of currents as a secret. They knew about them. They knew there was something out there that was allowing them to go faster. Either it be they were sailing ships to go conquer other lands or to give goods and from one place to another. They, like I said, they thought of it as a secret, and they didn't want to tell their people about this secret passageway that helped them get through the water faster than most other routes. All right, so Benjamin Franklin realized this back in the early colonies. You've learned about in your history class. He realized that ships that were coming to the colonies from the other side of the pond took a lot longer, like weeks longer, days longer, to get over from England, Europe, and then get over to what is now North America. But the ships going back didn't take as long, but that's because it's something called the Gulf Stream. The Gulf Stream goes in a clockwise rotation, and so it was faster for them to get from the United States or North America over to Europe. So eastbound voyages sailed with the current, but when they came back, they were against the current. And so Benjamin Franklin was one of the first ones to kind of realize that there was a reoccurring event that was probably more scientific than it was theory. Here's a video that shows different surface currents. You can see here we're in the Gulf of Mexico. You can see how the water moves and churns. The Mississippi has a huge thing to do with which way the water flows. But this that you see here, this thicker line of movement, that is the Gulf Stream. And there are different types of streams and currents that flow all around the world. You notice here, it's the equator. For some reason, we'll talk about later, I don't want to get ahead of myself, the currents do not like to cross the equator. And we'll learn about that in a couple of slides. And depending on if they are in the northern hemisphere and southern hemisphere, the waters typically flow in a certain direction. Now, every theory is not 100% perfect, so as you can see here on the eastern side of Africa, there are parts where the currents sometimes overlap the equator. A lot of currents also, as you have noticed, have gone with the lay of the land. They typically will not try to go through the land, obviously, so they'll go with the land, and so you'll have currents that go along each coast the same direction. Over here we have the California current, and currents change a little bit as they go into gulfs, into bays, but overall around the world they typically flow within the same pattern. Right, so here are some listed gyres and or currents. So we have the Gulf Stream here, the one that we're going to talk about the most. I take stuff from the Caribbean, the warm waters here, up the eastern coast, over here to Europe, back down through Africa, and then brings it back up through the Caribbean. This is why hurricanes flow off the coast of Africa and always come straight here to the Caribbean instead of going up into Europe or down into South America. Over here, we have the EAC, as you've seen in Finding Nemo, East Australian Current. All right, this is a real thing. It's on the east side of Australia. And if you look all around the world, they each have their own type of subtropical gyre or current system. And over here, as I mentioned earlier, here's the Gulf of California's current system. Right, so these are called surface ocean currents. They're kind of like rivers of circulating water. So yes, water can go from point A to point B in other sides of the world through evaporation and then through precipitation, but there are areas within the surface of the ocean where the water does flow in a constant pattern throughout the year, throughout the decades, centuries. They just follow the same surface current, and that's why they're referred to as rivers, as you can see in the previous video. The causes of these, there are two main causes of surface ocean currents. Main one is wind. It's the same thing that causes waves. The other thing is the rotation of the earth, and that was the thing I didn't want to give away earlier. It's called the Coriolis effect. That is why hurricanes in the northern hemisphere go clockwise, and in the southern hemisphere they go counterclockwise. But we're going to get more in depth to that later. All right, so there's a wind principle that comes with these currents, and remember these surface currents. Surface currents deal with wind and the rotation of the earth. So air moves from cold areas to warm areas. All right, this is typically true no matter where you are. So you have cold areas in the north and south poles, as you can see here. All right, and these things are going to want to move towards, as you can see through this arrow, the equator. Once they get warm enough, they're going to want to go back to the cold. So it's areas of high concentration and low concentration. Want to go from the place of warm temperature, you're naturally going to move to the cold area, and cold area back to the warm. As you can see through this diagram here, you have the equator along the middle. Typically, currents do not cross this. They will just go in cycles around and around, either above or below the equator. All right, so more about the Coriolis force or Coriolis effect. So it's Coriolis. All right, this is how objects move or seem to move. So if you throw something, typically it goes in a straight line. But if you look at it from a different perspective, maybe off the Earth instead of on the Earth, then you'll notice it has a slight spin to that, and that is because the Earth is always rotating. So if you look up here in this top diagram, change the color, let's see, purple looks good. All right, so this is the way it would look with the wind effects with a non-rotating Earth. Wind effects go straight down, they move straight down. But the Earth is always rotating, so it rotates 15 degrees every hour. So with that, instead of it traveling in a straight line, it's going to curve that 15 degrees, and that's what causes the currents to move in that clockwise position. I'm going to take away my video, and you can see that here from the North Pole down, it does curve about 15 degrees. All right, this is very important here. You do want to make note of this. In the right hemisphere, in the northern hemisphere, they move to the right, or should I say clockwise. Very important. And in the southern hemisphere, they move counterclockwise. And the reason I say this is important because this is why hurricanes turn the way they do. This is why our systems move in a certain direction, the storm systems. So remember, Coriolis effect, rotating Earth, and it causes things in the northern hemisphere to go clockwise and southern hemisphere counterclockwise. This is also why when you flush a toilet, it goes a certain direction. So as I mentioned earlier, the Coriolis effect is the reason why hurricanes have the spin that they have. The surface currents of the ocean spin the way they do, and wind has a natural spin. Because of that, there's some things that people didn't realize the Coriolis effect was affecting, like the bend in the path of missiles and or the bullets of snipers. Snipers have to take the Coriolis into effect whenever they are shooting or they will miss their target.
What's going on here? Every time I throw the ball straight, it seems to bend to the side. No matter what I throw, no matter how straight I throw it, the ball seems to be curving. Maybe it has something to do with this. That whole time I was spinning, which is why it looks like I'm about to puke. That curve is created by the Coriolis effect. You may have heard that it makes water in the bathtub spiral down the drain a certain way, or that it determines the way a toilet flushes. That's actually wrong. Those are not caused by the Coriolis effect. But the Coriolis effect is what makes hurricanes spin, and it's the reason why Jupiter's Great Red Spot is spinning the way that it is. So what is the Coriolis effect? Well, it's what happens when objects moving in a straight line appear to curve because you are rotating. And it affects all kinds of things. It bends the paths of missiles and sniper shots. But how does it work, and how does it create hurricanes? Right now, it seems like the ball's curving, but let's take a look at what's really happening. My friends and I put together this little experiment using a sort of spinning seesaw. Here, the camera's standing still. It's just hanging from the ceiling. And watch what happens. From the moment the ball leaves my hand, it's just going straight. Let's watch that again, frame by frame. Keep your eye on the ball. You can see it travels in a perfectly straight line. But what if you're spinning with the seesaw? Look at what happens when you rotate the footage so the seesaw stays sideways and everything moves around it. Now let's follow the path of the ball again, but from this new perspective. The trajectory looks completely different. Now let's watch this one frame by frame. From this rotating perspective, it totally looks like the ball is curving. That's crazy because you already saw that exact same throw. Watch it again on the left. The ball is going straight, but on the right, when you're rotating with the seesaw, the ball really looks like it's curving. You might be thinking, why should I care? I don't spend a lot of time on a spinning seesaw or on a merry-go-round. But you kind of are on a merry-go-round. The Earth is constantly spinning. Have you ever seen someone in a movie making fine adjustments on their gun? Well, one effect they're correcting for is the Coriolis effect. The longest sniper shot, which was over 3,000 yards, would have had to correct for a 1-foot deviation due to the Coriolis effect. So how does the Coriolis effect create hurricanes? Hurricanes form when air rushes from all directions into a low pressure region. So imagine there's a low pressure region between the two of us. Air is going to rush toward the center. Let's see what that looks like from space, from our camera that's hanging from the ceiling. It's not spinning, so the air, or in this case the balls, are clearly going in a straight line. But if you're rotating with the Earth, or with the seesaw, you'll see the air bend to the right. In the northern hemisphere, this creates hurricanes with counterclockwise spirals. In the southern hemisphere, it does the opposite. It creates hurricanes with clockwise spirals. This storm on Jupiter, which is actually bigger than the Earth itself, has been spinning for at least 200 years, largely due to the Coriolis effect. So when you're in a rotating frame, the Coriolis effect seems to exert a very real force on objects. But there is no force. What you observe is just a result of your perspective. And you might be wondering, if this is simply a product of your frame of reference, then could other forces like gravity or electromagnetism also just be products of your frame of reference? Of where we live in the universe or in the multiverse? For more on that, check out our video, Do We Live in the Multiverse?
So a really big and important surface current that we'll be talking about is the Gulf Stream. That is the one that is closer to home to us. It comes through the Gulf of Mexico, it goes up the east coast of the United States, and it makes its way over into Europe. It comes this direction. All right, once it hits here, it takes this warm water from the Caribbean, and it takes cool water from the pole, North Pole, and brings it down back to the equator near Africa, and then it comes back around. Once again, this is why hurricanes travel this direction. It goes back up. So this happens in the northern Atlantic Ocean. It brings warm water, like I said, from the equator up, and then it brings cool water down. Sometimes it forms something called eddies. This is circulating water that pinches off from the current. Move my video. You have eddies down here. Sometimes that water will pinch off, cold water, warm water, it separates, and it causes a little current within itself that moves off into the ocean, carrying a mixture of cold and warm water. Alright, so there are two different types of surface currents. You have warm surface currents and you have cold surface currents. So we have an example of the warm surface current, that would be the Gulf Stream. Right? Starts at the equator, works its way up, and eventually comes back down. Cold surface currents are like the California current, and they start up at one of the poles and then they carry the cold water down to the equator. Right, importance of surface currents, four main things. Migration. You typically hear migration of whales, it could be other smaller fish. Navigation, helps with navigating ships back in the day and now. It helps with the upwelling or mixture of nutrients, and it affects weather like hurricanes. All right, so now that we've talked about surface currents, different types, and why they're important, we'll talk about deep ocean currents. They flow below or beneath the surface, and these types of currents do cross the equator, and they move from north to south, and then once they get south and they warm up, then they become a surface current because they get warm, they come up to the top, then they'll work their way back around, they'll get to the pole, north or south pole, they'll get cold and they'll go back down. They're separated by a boundary called the thermohaline, temperature, haline salt. This causes the water to change in its density, which is why the currents either go at the from the depths up to the top and vice versa. In this video, I'm going to show you how temperature can affect the flow of water on the surface and in the ocean depths. So I've used red food coloring to represent warm water and blue food coloring to represent cold water. As you can see, the water is flowing to opposite ends. It is moving away from areas of cold concentration to high and vice versa. From this view, you can see the red, warmer water flowing on top and the cold water sinking to the bottom. If you want to do this experiment at home, all you need are plastic bags, a big container, and food coloring. Obviously, hot water and ice. As the water reaches the other side, it will start to sink when it gets to the cold side and rise when it gets to the warm side. As we can see here, we have some blue food coloring resurfacing to the top, and some of the red food coloring is sinking to the bottom. If I let this go on longer, then it would just keep going and going until all the colors were purple. This picture here is from when we got to do the lab last year in class. I'm so sorry you don't get a chance to do it this year. This side is where the hot water is. All right, so put hot water in this bag to warm up the water in the container. And on the opposite side, we have cold water. And what happens here is when you put food coloring in, the water is cold in this region, so it causes it to sink. But it's going to naturally move across the bottom of the ocean floor over to the equator, which is where the warm water is. This warm water is warmer, so it floats to the top, and it's going to travel all the way up to either the North or South Pole until it hits the Arctic shelf, and then it's going to cool down and it's going to sink. So here's a video showing the deep ocean currents. As you notice, they are crossing the equator, as you can see down here. This does help influence the Gulf Stream in a way, but as the warm water comes up to the pole, it hits the glaciers, the colder water, and then it starts to sink because of the change in the density of the water because of the salt mixture and the temperature change. That sinks down, comes a deep ocean current, and it is going to travel south back towards the equator. All right, because this water is deep, it's a deep ocean current, it's deeper in the water, it's not as affected by the sun, so it takes a little bit more for it to get warmed up to resurface as a surface current. These currents travel all around the world, and this is what we call a global conveyor belt. All right, a global conveyor belt. It is moving nutrients, it is moving animals, it is moving water all around the world, which is why it is called a global conveyor belt. I really like this video because it shows you the texture of the ocean floor, which is what we're going to talk about next in this unit, the ocean topography. Here's another diagram, kind of shows the continental shelves of the different continents around the world and where the surface currents, the shallow, warm currents go, and then the deeper, colder currents. And it is way more salty down here. Right, the importance of deep currents. Major thing here I want you to know is this a term called upwelling. It is bringing water up, upwelling, from the cold up to the top where it is warmer. It's allowing wind and stuff to mix it up, and it is moving those nutrients again as a surface current through warmer water. And so there are high nutrients here. All right, so it brings up the deep water. One importance. Forgot to turn my video back on, I'm sorry. So it brings up the cold water. All right, upwelling. It circulates nutrients, and this also moves things like plankton and larvae. Plankton and larvae are a main food source for a lot of large animals that we learned about in our endangered species project. Now we're moving on to tides. So we talked about currents. Last week we talked about waves, and now we're going to talk about tides. We've heard of low tides, high tides, different tides of the day. Most weather apps have a thing that tells you when the tides are, especially if you're going to the beach. All right, so a little bit more about tides. They are the rhythmic rise and fall of the ocean water. Rhythmic, back and forth. It's the same thing over and over again. Depending on where you live, depends on how many tides a day you have. All right, a high tide is the water coming in, high, water rising. And then the low tide is when the water leaves, or the water is receding. It's going away. All right, and slack tide is the vertical movement, or I'm sorry, it's when the vertical movement stops. So it is a time between tides where there's nothing happening. So here you see the same building at low tide and high tide. Some regions have tides that are so dramatic that there's a huge change, and you can see it in the boats and the other things there, and other places the tides vary so little that you can barely tell. Here's an image of a dock off a coast at high tide and low tide. They even have the sides of the wall painted about typically where the high and low tides end. There were people that had to study tides before they built here to know how high the wall needed to be in order to prevent a loss of businesses and structures. All right, so importance of tides. Anything we talk about is always going to have something important. Obviously, the importance of tides is something important for you to know. All right, so the importance of these tides. Expose and submerge organisms. Some organisms, like sea turtles, rely on the tides to bring them up to shore so they can lay their eggs and then bring their babies back out to the water. There's other organisms that rely on it. We have sea urchins here. Kelp relies on it. We have some fish that spawn on the surface. I don't want to give it away. There's a video later on. It helps circulate water into the bays and estuaries, helps mix that salt and fresh water, circulates food, it moves waste out, and it helps with spawning, helps allow things to grow, reproduce, etc.
One of the more exciting behaviors of tides is a phenomenon known as a tidal bore. This video shows a tidal bore moving up a shallow embayment south of Anchorage, Alaska called Turnagain Arm. Remember, this area has a tidal range of 34 feet during spring tides. When 34 vertical feet of seawater rises in 6 hours and 12 minutes, and then falls again in the same time, it can cause quite a flood and ebb current, especially in areas that are flat, where waters can be required to move inland hundreds of miles to achieve that height. Where waters already exist, such as embayments and rivers, these fast-moving flood currents can create the effect of a wall of water migrating uphill. It is an incredible spectacle to see, as the power of the water can cause a lot of erosion along the edges of the embayment or river. And it's a major navigational hazard for swimmers and boaters. Areas of the world that are prone to tidal bores and have large populations, like in China, usually have some kind of warning system to alert folks and give them some time to move off the river or bay until the tidal bore has passed. These video images are from various places around the world where these tidal bores exist. As you can see, some enterprising surfers have taken advantage of these long-lasting high waves and ride them. The world record is over 30 minutes for a single ride. Not all locations have tidal bores, of course. To get one, you need a large tidal range traveling into a low-lying coastal river mouth or embayment or narrowing. For example, we get a small tidal bore under the Golden Gate Bridge during spring tides. It has been known to overturn small boats, so it's wise to pay attention to the tides and be sure to stay away from this area when the flood current is coming in. This side-scan sonar image showing the depths around the Golden Gate Bridge illustrate the incredible strength of the tidal currents that run under the bridge. So strong that they have carved out a deep depression, 351 feet deep in fact, deeper than the edge of the continental shelf. Where is tidal range highest in the world's oceans? That honor goes to the Bay of Fundy in Nova Scotia, Canada, with a range of 17 meters or 55 feet. The high tidal range means that ships that come into this bay have to time their entry with the flood currents to ensure there is water at the dock when they pull in. When the tides go out, their ships are left exposed on the mudflats. Good time to clean the bottom of the boat, but only if it can happen in 6 hours or less. The fast tidal currents associated with this area are caused by water pushing 200 kilometers inland. One location along the St. John River is known for its reversing falls, which alternate their direction depending upon the direction of the tidal current. This push of water is so strong that it is used in some places to generate electricity on both the flood and ebb currents. How do tides affect marine organisms? When the tide is out, it's not just humans who head out in search of clams and oysters. The wildlife takes advantage of the low tide as well, including large populations of birds, but also mammals like raccoons, foxes, and bears. When the tide rises, they retreat to the land, and predators of the ocean move in search of the same crustaceans and mollusks. These predators include rays, skates, and leopard sharks. So feeding happens in intertidal zones when the tides are beneficial. That means that these birds and mammals feed by the tidal cycle, not by the solar cycle. You will often hear and see large flocks of birds setting down in these areas, even when it's the middle of the night, because it's the best feeding time. Submarine organisms, such as horseshoe crab, grunion, and turtles, breed, mate, or lay eggs according to the tides. This picture and video show a regular sight along the Southern California coast when the grunions swim up onto the beach at a high tide on a spring tide and lay their eggs. Why then? These are the highest tides available in every 2-week period. Sea levels should not get that high again for another 2 weeks, and that gives the eggs time to develop before the water returns to take them back to sea. Turtles will lay their eggs far from the water's edge, but by arriving on the high tide, the mother turtles do not have to travel so far up the beach to get to the dunes and the best and safest nesting areas. How do these fish, crab, and turtles recognize the spring tides? Most likely by the sight of the full moon. Pause now.
Tides are very long, slow waves. They have a wave period of about 12 hours, and one tidal wave takes over 24 hours to complete. If you look over here at the diagram off to the right, you can see how the Earth's rotating throughout the day, how the high and low tides change, and where the moon is being repositioned or moving throughout that day. We will see more about this in the activity that you will have on Google Classroom. What causes tides? Tides are produced by a gravitational attraction between water on Earth, because it has positive and negative charges, and the moon and the sun. These forces deform, quote unquote, the Earth's surface water, causing two bulges to form. One goes towards the moon and the other one goes on the other side of the planet, especially if they are lined up. So once again, the gravitational pull of the sun and the moon on Earth is what causes the tides to occur. The closer the moon is, the higher the effect is. It acts like a magnet, and this is what causes a tidal bulge. And you can see that here where the water is bulging out. Just an example of how the moon and the Earth rotate around the sun or orbit around the sun. I know it's been a while for some of us since we've last seen something like this. This will make more sense as we go on throughout our notes. So there are different types of tides we're going to talk about. The first one is a spring tide. The spring tide is when the moon and the sun are in direct line with one another, and this causes a higher tidal range. It has the gravitational pull from the moon and the gravitational pull from the sun pulling the tides in the same direction, causing a very, very high tide. This happens once every 2 weeks, and it has to deal with the phases of the moon. Opposite of that, we have what is called a neap tide. The neap tide occurs when the moon and the sun are at right angles. Because they are pulling in opposite directions, they cancel each other out. All right, this causes a weak pull on the water on Earth, and this is when the low tidal range occurs. And tidal range is the difference between the high tide and the low tide. So I'll go back for a second. Can't go back. For the spring tide, that means the high tide and the low tide. Let's say the high tide might be at 100 feet. It's just a random number. And the low tide is at 10 feet. That's a tidal range of 90 feet. But here during the neap tide, an example would be that the high tide might only go up to 30 and the low tide is still at 10. So the tidal range is only at 20 feet. And that is where the tidal range differs. So here with the neap tide, because the pools are going in different directions, the range between the high and the low tide are lower. So here are the phases of the moon, just a little reminder. The phases of the moon do affect the spring and neap tides, and each of them happens every 2 weeks. So together you have one spring tide a month and one neap tide a month. You can use the phases of the moon to predict when these tides are going to occur. So here is something from the NOAA, for tide prediction. This is an example of one in San Diego Bay. And you can tell here when there's a full moon and a new moon, the range is a lot higher. So here we have full and new moons, and the ranges are a lot larger than they are during a quarter moon. Alright, so this would be a spring tide, and this area would be a neap tide. So more about tides. This one is the one that differs based on where you live. The other ones are determined on the moon. Alright, so you have semi-diurnal, di-2, tides. Semi-2, di-2. You have 2 high and 2 low tides a day. Alright, and this deals with the Earth moving around, as you can see here, as it rotates. This is the most common type, happens in most places around the world, and this is because not so much the moon and the sun, but how the Earth is moving. So semi-diurnal. You have mixed semi-diurnal tides, so it's a little mixture of, it has 2 high and 2 low, but instead of it being the most common one, oh thank you, Champ. This one is mixed because of the Coriolis effect in maybe land masses, areas where there are bays and bigger structures that might be blocking the water. And then you have something called diurnal tides, not semi, just diurnal tides. That's number 3. That is 1 high tide and 1 low tide a day. These are a lot less common, and you typically only see these in the Gulf of Mexico and Asia. So we are part of a rare group of people that live in an area that have diurnal tides, so we only have 1 high tide and 1 low tide a day. It's pretty cool. So here's a map showing you the different tides around the world. The red one is the semi-diurnal tides. It's the most common. As you can see, most of the world has those red outline, which means it has semi-diurnal tides, 2 high and 2 low tides. Diurnal tides, yellow, are here, parts of Asia, and then the Gulf of Mexico. And then some areas you have mixed. Those are typically found, we have here along the western coast of North America. We're here in the Caribbean. Alright, it's just a mixture of the two. You're never going to have a perfect world where it's just one or the other. There's always going to be a mixture. Alright, second to last slide. The Lorentz plant off the coast of France is an area where they get semi-diurnal tides. So they get 2 high and 2 low tides a day. So they take advantage of these tides, especially in this bay region, and they like to generate a lot of energy from their tides. So this bridge you see here is packed and equipped with generators that take the energy as the tides come in, and as the tides come back out, sorry, it's messing up, and that happens, like we said, twice a day. 2 high tides, 2 low tides. So take advantage of both things. Champ and I did want to say before you get a little short clip on your last slide, hope you enjoyed our lecture on tides and currents. Champ says bye. Don't forget to do your assignments on Google Classroom.